Okay, moving on to the 2005 differential equation FRQ. In this problem, we are given a very simple differential equation in terms of x and y. dy dx equals 2x minus y. First question, on the axes provided, sketch a slope field for the given differential equation at the 12 points indicated, and then sketch the solution curve that passes through the point 0, 1. So I won't go through and find every single one of this, but I'll walk us through how we would start doing this. We've got 12 points here, so what we do is we'd find one of these points. So I'll just take maybe this point right here. At the point -1, 1, what we would do is we would plug that point into the differential equation. That would give us 2 times -1 minus 1. And that would give us a slope of -3. And so what I want to do then at this point is I want to draw in a slope that looks like -3. So it's going to be fairly steep. It doesn't have to be perfect, but it's going to be steeper than -1, which should be more of like a 45. I'll try another point. I'll try this one up here at 1, 2. At this point, we have 2 times 1 minus 2. That's going to give us a slope of 0. Remember, that would be a horizontal line. And I'll just try this point here as well, 1, 1. At 1, 1, we would get 2 times 1 minus 1. That would give me a slope of 1. That's where we have that perfect 45 line. So I'll just go through and kind of draw in these other ones. You can check your work. And again, when we start talking about these ones being steeper than others, as long as they're following a pattern of steepness, that's what counts. It doesn't have to be exact. So your solution curve or your slope field should look something like this. And if you get all of these points on, so the points alone, having the slopes here, you're going to get 2 points for this part. Now, the part where it says draw in the solution curve that passes through the point 0, 1, so I'm going to put a point there at 0, 1, because that's what it gives me, and I'm just going to follow this curve. So it looks like the curve here is going down, but then as it comes over here, it shoots back up. So we kind of get, it drops down to a minimum and then comes back up, and up here it's shooting kind of in that direction. So something along those lines, if you get that correct, that's another point. So this first question was worth 3 points, a very doable 3 points. Part B says the solution curve that passes through the point 0, 1 has a local minimum at x equals ln 3/2. What is the y coordinate of this local minimum? What we're going to do is we're going to use the derivative they gave us. So in this problem they told a little technical difficulty here. The derivative that they gave us is that we have 2x minus y. Well, we know that at a minimum, what happens, or actually a maximum or a minimum, we know that dy dx must equal 0. So knowing that, if I know that dy dx has to equal 0 at this minimum, and I know the x value, I can plug stuff in and actually solve for what y is equal to. So I'm going to plug in 0 for dy dx, and then for my x value, I'm going to plug in ln of 3/2. And then I'll do minus y. Now what I can do is I can solve this for y. Very simple. I'm just going to add, I'm going to bring the y over, and this implies that y is equal to 2 times ln of 3/2. And that's my solution. This question is worth 2 points, and you get a point really for this part. This is the important piece, that recognizing that at a minimum the derivative is equal to 0, and then when you actually get your y value for another point. So it's the 2 points for part B. Question C, it's another Euler's method question. Let y equal f of x be the particular solution to the given differential equation with initial condition f of 0 equals 1. Use Euler's method starting at x equals 0 with two steps of equal size to approximate f of negative 0.4. So I will set up that table here. We've got a column for x, y, y prime, delta x, and delta y, which is equal to y prime times delta x. Our initial point, they give that to us, that is the point 0, 1. Now our goal is to use two steps of equal size to eventually get to negative 0.4. If I'm trying to get to negative 0.4 to get my final y value, then my middle step has to go to negative 0.2. What this does is it gives me a delta x of negative 0.2. And that's an important piece. I'll also just rewrite down our dy dx as 2x minus y. Now we'll start filling in the table. At the point 0, 1, dy dx at 0, 1, I get 2 times 0 minus 1, which gives me negative 1. My first y prime is negative 1. I multiply negative 1 times negative 0.2, and we get positive 0.2. That means I add 0.2 to my 1 here, and I get 1.2. Now I plug in the point negative 0.2 and 1.2 into the derivative next. dy dx at the point negative 0.2 comma 1.2, and we get 2 times negative 0.2 minus 1.2. That gives us negative 1.6. And then we have to do some crazy multiplication, all of this in our heads, of course, because we don't have our calculators. Negative 1.6 times negative 0.2. Just think, 16 times 2 is 32. I move the decimal place over twice. This gives me 0.32. That gets added to 1.2 to give me 1.52, and that is my approximate solution. So f of negative 0.4 is approximately equal to 1.52. How many points? 2 points. 1 point for the answer, 1 point for the work. And that gives me part C. So at this point we're up to 7 points out of the 9. So that leaves 2 points for this last question. Okay, question D. Find the second derivative in terms of x and y. So we have to be careful with that. We have to make sure we plug in our dy dx for that. So we'll do that first, and then we'll tackle the rest of this question. So we know that dy dx is equal to 2x minus y. If I do the second derivative with respect to x, that means I'm going to need implicit differentiation when I deal with the derivative of y. The derivative of 2x is still 2. Derivative of minus y would be minus dy dx. I'm going to plug in dy dx, the 2x minus y, for this dy dx. So I get 2 minus 2x minus y. Or I could write that as 2 minus 2x plus y. And that is my second derivative in terms of both x and y. And we need that for this first part of the question. Now, what does the second derivative tell us? So we can get some information from the second derivative that will help us answer this next part. Determine whether the approximation found in part C is less than or greater than f of 0.4, negative 0.4. Explain your reasoning. Euler's method is really a linear approximation. It's a numeric method for testing a linear approximation. So if we think about what the second derivative can tell us about a linear approximation is we have to think about the concavity. If we have a concave up graph, the linear approximation is an underestimate. Okay, right? So this would be an underestimate. If we have a concave down graph, the tangent line is an overestimate. All right, we're gonna have to go to part 2 of this video. My pen stopped working.